today and tomorrow we're going to talk about this thing called Riemann sums. So I already told you that in chapter 3, in chapter 2 we did the derivative. Chapter 4 is going to be about going backwards, like antiderivative. So even on your timeline you can see that's what we're doing next week, the antiderivative. Okay, Riemann sums is a nice way to bridge what you do know already about specifically geometry. It's going to look more like a geometry lesson, and how that relates into calculus. So really, today and tomorrow, I'm not really going to be doing a lot of calculus, although on the AP exam, they are going to expect you to know these strategies. Okay, and I'm going to show you many ways, between today and tomorrow, I'm going to show you many ways to make estimations on these problems. Okay, so on this first one, it's talking about coal gas, okay, being produced. There are pollutants, okay, in this gas. But they get removed by scrubbers. But as time goes on, these scrubbers don't work as well, and more pollutants get released into the air, which is bad. So these are the measurements. So I want to make sure you really understand these measurements. Okay, imagine that this is my job to measure these pollutants. So like today, we'll just say starts the first month, okay? And today, no time has passed. And I get out a nifty little gadget that measures that the speed at which the pollutants are being released is 5 tons per month, okay? And then 1 month from now, after 1 month has passed, I take that measurement again, but now it's 7 tons per month. So this is totally aligned with the fact that they said the scrubbers are going to become less efficient. There's going to be more and more pollutants, okay? So the first thing they ask us to do is to make an overestimate and an underestimate of these pollutants. This right here is a rate, okay? What we're going to be doing is kind of going backwards from that, okay? They're asking us something where our answer isn't going to be tons per month. Our answer is going to be just this many tons. All right, so saying during the first month. So we're just going to take one thing at a time. We're going to do this, and then we're going to see how we do it for more data. So if between today, which starts the very beginning of time, time equals 0, in other words, to the first month, you know, it starts out as 5 tons per month. It increases to 7 tons per month. So what would be an overestimate? What do you think is the largest amount of tons of pollutants that could have been released during that 1 month? Don't think too hard on this one. No, look. You're still thinking too hard.
12.
7. Okay, so let me explain why. 7. All right. At the beginning of the month, I'm not telling you that it's 5 tons at the start. That's not what this is saying. It's saying that at time equals 0, these pollutants are being released at a rate of 5 tons per month. So if they were to continue at that same rate, it would be 5 tons over the first month and 5 tons every month, okay? But that's increasing. So the highest, 1 month from now, it goes all the way up to 7 tons per month. So imagine this. Imagine that it's not this smooth, it is a smooth curve, but imagine that I take the measurement today and it's 5, and then immediately it increases to 7 and kind of rides out 7 for the whole first month. That's when, if it's 7 tons per month during the whole month, then 7 tons is my answer for 1 month. So then what would be my underestimate? 5. Okay. Some of you are not really sure what I'm asking, and so let me rephrase it this way. I'm just asking you that if we only look at the lower or higher speed, and that was the case all of the time, how many tons of these pollutants would be released, okay? And so we have this left number and this right number to choose from for that first month. All right, now if we were including like the second month, okay, then we would have to do a little bit more because we have multiple months to look at. All right, always if we were looking at 1, we'd take the lower number for the under, the higher number for the over. That's all I'm looking at here, okay? And so that's important that you can kind of at least get that before we move on to this next part. because what we're going to do now is for the whole 6 months. Now, you can't just say 5 and 20, because remember, those are rates. So if this was at 20 every single month, then we have to multiply that, by 6. So there's more going on when you look at multiple months at a time. So this is where a graph would really come into play. So first of all, if we're looking at our two variables, what's my independent variable? Months. Time and months. And then my dependent variable would be the rate the pollutants are escaping. And I'm going to just put the units here, tons per month. So what happens when you multiply tons per month times months? What units do you get? Tons. So essentially, that's what we're going to be doing. We're going to be multiplying x times y. And really what this is going to look like is area. Okay, so let's go ahead and plot these points. So I'm going to go ahead and plot 0, 5, 1, 7, and so on. This, I'm just going to expect everybody's really good at, because you guys have been doing this for a long time. One way this problem is easier than it could be is that we're only going 1 month at a time. The data, though, that's given could be every 2 months or every 5 months or something like that. That would end up making this problem a little bit harder, but we're just, all of these units down here are 1. So just, I'm going to note it now, because the next one we're going to do, it's not going to be like that. Okay, I'm going to go ahead and scroll like this so you can see this just a little bit better. All right, now what we want to do is if we were to connect these in a curve, okay, what I want to do is find the area under the curve. Now, have you ever been asked to find the area under the curve?
Yeah.
Yeah. Most of you would say you've seen it many times. You all should have seen it at least once, because I've asked you to do this before on one of the after parties. Okay? Now, we are going to learn a calculus way to do this, the antiderivative. But let's use what we already know first. And these are things the AP test is going to ask you about anyway, so it's good to go through for that as well. And the easiest shape really to deal with is a rectangle. Okay? So, if I make a rectangle, and I want to go ahead and I want you to write the word left up here. If I make a left rectangle, meaning that at each of these blocks I have a rectangle, and the way I determine the height of that rectangle is from the left point. In other words, from 1 to 2, I could consider either of these points. I'm going to pick the left point to make my rectangle. And the right one is coming up as well. So if you look at all these rectangles, what I could do is find the area of these rectangles. Area of rectangles is super easy. Okay? And I'm not going to go between 6 and 7 because it doesn't say into the 7th month. It's just in the first 6 months. So how many rectangles do I have? I have 6. How many data points do I have? 7. That's always going to happen that way. You're always going to have 1 extra data point here. Okay? So that's okay that we're not using this one for the left. So if I were to find the left rectangles, meaning I'm going to find all this area, do you think that would be an under or over estimation of the real answer? Under. Because I'm using the smallest value during each month instead of using the largest value. So in this case, left is going to be an underestimation. Do you think left will always be an underestimation?
Not necessarily. Maybe it's going down.
Yeah, so if the points are a decreasing pattern, then the left point would actually be higher than the right point, and therefore it would flip-flop on you. So don't memorize that left is under. It's not. It is in this case, though.
It's just under because you're not connecting the points. You're not measuring that little area between.
That's right. If we were to connect these 2 points right here, there's a little triangle that, it's not really a triangle because it's a curve, but there's a little bit that I'm not including. All right, so let's think about how we would find this area. Yeah.
If it is decreasing, you would still have that
You're right, but I would be over. We'll do it in a second, because I'm going to do the right triangle, and that's going to answer your question here.
Okay.
All right, so to find each rectangle, because the base of these rectangles is 1, again, that makes this easier, because base times height, all I really need to do is list out all the heights and add them up. Okay? So then the first height would be 5, and then 7, and then 8, 10, 13, and 16. Notice that I'm not writing 20. I have no rectangle that has a height of 20. Like, I get that I wrote that right there, but that's not part of that rectangle. Okay, how many numbers do I have? 6. That should line up with how many rectangles you have. Again, 1 less than the number of data points. So if you add all these up, what do you get?
60.
Not quite. Feel free to use your calculators. 59. And what are my units here? Tons. Okay, so I really want to make sure you understand why we can do this to make an estimate. We're just multiplying tons per month times the number of months. That gives us the number of tons, which is what they asked. Make an overestimate and an underestimate the total quantity of pollutants. Okay, so then now what we're going to do is we're going to do the right-sided rectangles, which should be an overestimation. Now, a really easy way to figure out if you did this right is my answer to this next part should be bigger than 59. If it's not, I messed up somewhere, either in my labeling or my number crunching or something. So let me show you what I mean by this. It means that, like in our very first thing we did, instead of saying 5 is the number I'm going to pick for the first month, I'm going to pick 7. Okay, in other words, I have 2 points to choose from. I'm going to choose from the right point each time. So all my rectangles are going to be a little bit bigger. Another way to kind of think about this is that each rectangle kind of just moved over 1 slot. Do you see that?
Yeah.
You see how the second rectangle is now taking the place of the first one? The third is taking place of the second one, and so on. The first rectangle is completely out, but then my 6th rectangle is in there instead. So it's kind of like, you can think of it 2 ways. A little bit added on to each rectangle, or replacing the smallest one with the largest one. And so if we're going to add these up again, because the base is 1, all I have to do is really list out the numbers. So that's going to be 7 plus 8 plus 10 plus 13 plus 16 plus 20. Again, 6 numbers because there's 6 rectangles. 74. And again, over should be bigger than your under. If it's not, you messed up somewhere. It's a really nice built-in check. It won't fix every mistake, but it will definitely catch certain ones that I see happen. All right, now both of these are not really great answers. Okay? Now, this is nice because it gives me a range. If this is my job to report back to my boss how many pollutants I think have escaped in the last 6 months, well, then I could say it's between 59 and 74, and maybe that's the acceptable range. Maybe it's not, and then we got to figure that out. But he really wants me then, or you know what? This is 2013. I'm going to call my boss a she this period. She really wants me to get a better answer. Okay? What do you think I could do to really make my answer more like probably what the true accurate answer is? Average, yeah, take the mean, take the average. What this would do is, think about it this way, it'll cut this difference in half, okay? You think about it almost like this way. So we could do that work, okay, and then redo everything, or what's much, much easier, since I already did this work over here, is 59 plus 74 divided by 2, which gives us 66.5 tons. Now, you could have averaged the 2 numbers to begin with. Like, let's say we didn't do all that pre-work up here. We didn't do the under and over. We just went straight for this one. then, you know, there's other things we could do. But since we already did this work, we can just take the average of the two. Okay? So out of these three, which is the best answer so far? 626.5. Now, do you think that answer is exactly accurate?
No.
No. It's probably going to be a little over, a little under. Do you think there's any way to know which one it is?
Could you find like a derivative?
You could use some things with derivative here, in particular, the concavity, determining the concavity of the graph.
Yeah.
Whether or not the graph's curve dips below, and that we're going to do this in a minute, but you could use concavity, which is second derivative, to then determine if this answer is good enough or not. Okay, so we see right side estimate, left side, all that. Okay, let's move on to another problem. All right, so this is the airplane problem. Anybody in here jump out of an airplane before?
Yeah.
Okay. You're crazy. It's okay. But some people like that kind of thing. So you jump out of an airplane, before your parachute opens, you fall faster and faster. So your velocity is increasing. But acceleration is decreasing as you fall because of air resistance. So here's what we're assuming, is that as you're falling, you're like this. Okay? You're not wearing one of those pointy helmets and like trying to speed to the earth, okay? You are working against the gravity here. It doesn't mean that you're falling slower. It just means that you're not speeding up as fast as gravity could cause you to do. All right? And so, anybody want to tell me what they think the concavity of this graph is going to be based off of that?
Down.
I mean, yeah.
We're decreasing, but I'm sorry. My velocity is increasing, but my acceleration is decreasing. And my acceleration is my y value. If you don't know, that's okay. Okay, let's see. Let's see if you're right. I will tell you, on most of these, you're not really going to know unless you look at these numbers. But intuitively, you may have an idea of which one it should be. All right, so over here we have meters per second squared, and down here we have seconds squared, so, or just seconds, sorry. This is not position versus time, or even velocity versus time. They are giving you acceleration values. How they came up with these values, I don't know, some measurement or something, okay? So then we're going to start the same way we did before. We're going to plot the points on the graph. I want you to be thinking, though, as we go through this problem, could you do this without drawing a graph? And, like, if you notice the patterns and all of that. The graph, though, is definitely very helpful. So when you're plotting these points, don't worry so much about being really accurate, because we're not going to use the graph. We're going to use the graph as a guide. We're going to use the table, those numbers on the table, to really do this. Also notice that my points are spread out so that they're two apart, unlike the last one. Yes, Brett?
Are we going to reach terminal velocity in this? Or
What do you think?
eventually, yeah.
So, we're not, and I'll tell you why, because they don't tell us.
Oh, okay.
And the truth is, it doesn't even really matter, because all we're going to base our information on are these numbers. I don't even care what happens after 10. Maybe 10 is when you're supposed to pull the parachute cord.
Okay.
But the good thing about these kinds of problems is when they don't tell you something, you didn't need to know it. Whereas in physics, you rely a lot of times on background information. In calculus, you kind of the same type of problems, but they don't. On the AP calculus test, they're not assuming you know deep physics here. They're assuming you know how to do the calculus. Okay, so what I would like for you guys to do is we're going to split it up, and half of you are going to do the left and half of you are going to do the right, but let's make sure everybody's on the same page. If we were to do the left, if you're going to do the left, okay, what you would do is you would say your first rectangle here is how high? 9.81. And so what's the area of the first rectangle? Is it 9.81?
No, it's
9.81 times 2, because each rectangle has a width of 2, or a base of 2. Okay? How many rectangles are you going to have? 5. Remember, it's 1 less than your number of data points. All right? Are the left people here going to be under or over? Over. All right. So I would like all the guys in here to go ahead and do the left, the over. All the girls, okay, you're going to do the right, which we know should be under. All right, and so for girls, just make sure you're off to a good start. The first rectangle you have should be whatever 8.03 times 2 is. Because if you're looking at this first section, you're choosing the right number. In this case, the lower number. So go ahead and figure out whichever one you're assigned. If you think you have time to do both, do both. Practice. And when you're done, find somebody around you can check with. Okay, so for some of you, you've been working a little hard for your answer. If you're going to multiply all of them by 2, could you just multiply the whole thing by 2? Okay, so I was trying to see. Anybody think could do that on your own? Okay, good. Now you know, though. All right? It's not wrong if you multiply each number by 2 and then add them up, but you could definitely do that here. Okay, it could save you a little bit of number crunching. So what'd you get?
68.32.
68.32. So now for the really good question is, what are your units? Meters per second. Yeah, because remember we're multiplying meters per second squared times seconds. One of the seconds is going to cancel out, the other one's not though. The other thing is they tell us we're finding speed. Okay, so girls, same thing. You could have just multiplied the whole thing by 2. It would have saved you a little bit. And what'd you get? 55.92, and again, meters per second. Okay, so again, under is lower than the over. That should always happen. If it doesn't, something went wrong somewhere. All right. So B says get a new estimate by taking the average. Okay, this is just like what we did before. Neither of these really is that good of an answer, and so we're going to add them up. Divide by 2. And so far, this is our best answer, 62.12 meters per second. That is your speed at this point right here. It's not your speed throughout your falling. Remember, that speed is increasing. You're falling faster and faster and faster. Okay, so here's my next question. What if, okay, I'm going to use a different color here. Instead of rectangles, I connected the dots and drew this shape. This is a trapezoid. Do you think the trapezoid is more or less accurate than these rectangles? More. Do you think it's more or less accurate than this average? Okay, most of you are saying more. I heard a couple lesses, and I saw a few. I don't know. All right, so that's what we're going to do next. Okay, now, and if you look at it, it looks a lot more like what we're really trying to find, right? We're trying to find the area under this curve. And so I was going to ask y'all again, do you think this is concave up or concave down? Up. Now here's a big clue if you don't see it. Are the numbers getting closer and closer together? Is it flattening out? Yes. That's like an exponential decay almost. That's a concave up. That's, you know, and a lot of these tend to be concave up. Not always, but this graph is concave up. I'm even going to write this here because this is going to play into the next thing, which is use the trapezoid method to estimate your speed. Trapezoid method just means find the area of these 5 trapezoids. What does the concavity of the graph of acceleration tell you about their estimate? All right, so one thing about trapezoids is people freak out. 6th grade teachers, I feel they did something to you guys. They told you trapezoids were hard or something. All right, trapezoids are not difficult to find area of. A trapezoid is just a rectangle, but instead of one base, or the 2 bases being the same, they're different. So all you got to do to find area of a trapezoid is to average the 2 bases, add them up, divide by 2, and then multiply that by the height. That's all you got to do to find area of a trapezoid. Trapezoids, we use them a lot, particularly here, but they're very useful in calculus. Normally we have like 1/2 in front instead of over 2, but those two things mean the same thing. So when we find the trapezoid, area of the trapezoid, let's think about our first trapezoid here. Okay, now the height is actually the base because it's been propped up on its side. The way you can keep this straight is the 2 bases should be parallel. Well, this side down here and this side up here are not parallel, and you know what? I don't know this segment. I would have to use Pythagorean theorem to find it, and I don't want to do that anyway, so it's good I don't have to. The 2 bases, though, are just your 2 y values. So when you're trying to find the area of the trapezoid, we're going to add up 9.81 plus 8.03. These were the 2 bases. We're going to divide by 2. That's taking average of the base. And then we're going to multiply by the height, which is 2. Now, this will not always happen where these 2's cancel. All right, and I'm not doing 2 times the whole thing here because, look, that's going to make that cancel. It's going to make it easier for you to type this in. This right here is nice, okay, because these are going by 2's. They could be going by 1's or 4's or 5's or whatever, okay? So let's continue this. We're going to have 5 total trapezoids. All right, so the next one would be 8.03 plus, sad that I have most of these numbers memorized, 6.53. Divide by 2 times 2. Again, that divide by 2 times 2 is going to cancel. My third trapezoid is going to be 6.53. Notice the repetition and pattern of numbers. This is useful because if you don't have a picture, you want to still be able to do this. And drawing a picture could be time consuming. All right, so that's the third one.
Okay, I was right.
Some of you are faster than me. You already figured out the answer. There's the 5th trapezoid. Again, those 2's cancel. And then our final trapezoid and if you notice, see these numbers at this point, it looks a lot like our rectangles. In other words, there's two 8.03s, there's two 6.53s, there's two, 5.38s, there's two 4.4. The only thing that's different is on our underestimation, there were two 3.61s and no 9.81, and on the over it was the other way. Two of these, none of these. And so, anybody already add all these up yet?
62.1.
You get the same thing. So my question is, do you think it will always happen that way? Was this just like a major coincidence in the day, or what?
I think it always be. I think shouldn't it be the same as the average between the 2 points? Because it's
Yeah, I mean, think of it this way. You're averaging the bases each time.
Yeah.
Before, we were keeping the bases the same and then taking the average at the end. All right? Now, which do you think was easier to come up with? The red 62 or the green 62?
definitely green.
Okay, you're all going to have your own opinion. There's no right answer to this. To get the red one, it's a 3-step process. To get the green one, it's a 1-step, but you had to do trapezoid. You need to be comfortable with trapezoid method because on the AP test, they are going to tell you, use the trapezoid method. You got to show your work and everything. Okay? So then back to my question about concavity. All right. I just want to know, what do y'all think? Do you think my real answer, do you think 62 is an over or underestimation of the real answer, the true answer that, like, we could say only God knows or something like that? You think over? Do you have a reason, or do you just feel it in your gut? Yeah?
I'm feeling it.
Down, and we're doing straight.
Yeah, that's what she means. So imagine this, look at this trapezoid right here. We're finding that trapezoid right there. But the true trapezoid actually was dipping below, right? It was concave up. Okay? So what I really should be doing is only finding this area right here. So I actually found more, because I'm kind of like slicing through and I'm using lines instead of curves. I found a little bit more than I needed to. So this was concave up, therefore it was an overestimation.
Isn't there a way to like find the root of each of the curves though, and then?
You're right. Well, what we're going to do is I'm going to give you a way to do this like the way we did derivative, but we're going to do antiderivatives because we're going backwards. Integral, yes. Yes, Ashley?
So is it safe to assume that whenever it's concave up, it'll always be an overstatement, and whenever it's concave down, it'll always be an understatement?
For trapezoids, yes.
Okay.
Now, if you start doing left and right rectangles, the concavity really doesn't play into it. Although the average would fall under the same category as the trapezoid. Okay, so we're going to skip this page for right now. I want you to go to this one, number 5 in your packet. Not really going to get into this too much. But this is kind of the next phase of Reimann sums. What are we missing here? Points. We're not given the table. However, we are given a function. So could we make a table? Yes, of course you could, especially with the calculator. So in that sense, it's not different. Now they also tell us, because they say use 4 equal subintervals. All right, this is saying like 4 rectangles or 4 trapezoids. How can we make our answer more accurate? And my question is like going on that thing having to do with the number of rectangles, the number of subintervals. What makes my problem more accurate? Smaller intervals, so more rectangles, more trapezoids. Because if you think about it, a curve, if you zoom it way in, looks like a line. And the more you zoom in, the more it looks like a line, the flatter it becomes, and so that's how you can do that. And these trapezoid sums are actually really close to what these are in real life. which we still don't have a way to do that yet, but we will, and it'll be, but we'll have a method of doing that, and we'll need the function in order to do it. Some of you may already in your mind kind of have already figured out, like if this is already the derivative, what would have been the original function? We haven't done that yet, but you can kind of already start to think that way a little bit. Okay, so this is going to be your homework tonight. Oh, let me stop the video. Well, I'll leave it on for anybody who's watching it. You're going to do numbers 1, 2, and 3 for your homework tonight. There is more to do in this packet, but I just want you to do homework day 1, numbers 1, 2, and 3.